First thing I want to do in this video is define what we mean by the word radical. Radical is the algebraic expression for square root, so you'll hear me say that a lot today. And the big difference between what we're doing with square roots today and what we've done in the past is that we're not going to be plugging in square roots into the calculator today. We're going to be simplifying these without using a calculator and without getting decimals for answers. And we're going to do that by thinking about factors that are perfect squares, like 9 and 16 and 25, things that we can take the square root of in our head. So let's look at our first example A. We have the square root of 192, and we're going to have to think about some factors that are perfect squares that are factors of 192. There is only one pair that works in this case, and that would be 64, which is a perfect square, and 3. So I'm going to rewrite 192 to look like 64 times 3, and I'm going to put that underneath the radical, and what that allows me to do is to kind of break it apart. Since we're multiplying 64 and 3 underneath, if I give them each their own radical and continue to multiply them, this expression and this expression mean the same thing. And what the last expression allows me to do is actually take the square root of 64, and we all know that that is 8. And if we look at 3, I can't do that in my head. I'd have to use a calculator for it, but since we're not using calculator today and we don't want decimal answers, we're going to leave the 3 underneath the radical. There's nothing else I can do with that in my mind since 3 doesn't have any factors that are perfect squares, and so my final answer is going to be 8 radical 3, or 8 times radical 3. Same thing for our B example. Now this is different because we have a term on the outside, but what I'm going to do is leave that alone for right now, and I'll come back to it at the end. So we're doing the same thing. I'm trying to think of perfect square factors of 300. Some of you might have already thought of it. There's only one pair that works for this one also. That would be 100 times 3. 100 is our perfect square here. Now in our brains, we're thinking about splitting it apart. So we have 100 underneath a radical, and we have 3 underneath a radical. 100 is the one that's easiest to take the square root of, so let's do that. Here is where I'm going to work with my negative 5. This is negative 5 times radical 100, and we said that that will simplify into 10. And so our last step is actually using our negative 5. Negative 5 times 10 is negative 50. So our answer will be negative 50 radical 3. Example 2, we're going to have to remember some more stuff from factoring. If you'll remember when we were talking about perfect square trinomials, sometimes we would take the square root of a variable that had an exponent, and when you do that, we have some easy results here. We said that the square root of n squared was n to the first, square root of n to the 10th is n to the 5th, and if you'll notice the pattern here, all you're having to do for even exponents is just divide by 2. And as you can see from our statement up here, any even exponent is a perfect square. So as long as you have an even number for your exponent, you can take the square root of it and then get a solid answer. Something that's not going to be crazy. So let's take a look at our example 2a. Some of you might have noticed right off the bat that we have an a in here and we have an odd exponent. So I'm going to show you what to do when you do have an odd exponent, since the even exponents up here are pretty simple to work with. So let's take a look at the inside here. Since example 1 worked with numbers and we have a coefficient of 45, let's deal with that first before we worry about our variables. So we are thinking of factors of 45 in which one of them is a perfect square. And the only pair that works for that is 9 and 5. 9 is our perfect square. Okay, now the problem for this one comes with our a to the fifth. I need a to have an even exponent. So what I'm going to do is break up our a to look kind of like our factors here. I'm going to multiply so that I have two a's inside. And what I'm going to do is I want one of my a's to be an even exponent, and the other one, it'll end up being odd. And I'll show you what's going to happen. If I have a to the fifth, and I subtract an exponent of 1 from that, instantly I get an even exponent, right? If we take one of those away. So if I make one of my factors an a to the first, my other a is going to turn into 4. And I'm going to have an even exponent. And just to double check, a to the fifth can be written as a to the fourth times a to the first, because if you multiply bases, you're adding exponents. 4 plus 1 is 5. So I haven't done anything to change its value. This here is still a to the fifth, just like 9 times 5 is still 45. So let's go ahead and take our square roots here. Let's look at our perfect squares. 9 is a perfect square. We said that a to the fourth, since it's even, that's a perfect square. So we're going to take the square root of those two things. The square root of 9 is 3. The square root of a to the fourth, all we have to do according to this shortcut up here, we're just dividing it by 2. 4 divided by 2 is 2. Inside I have a 5. That's not a perfect square. A to the first, this is odd. That is not a perfect square, so I'm going to leave that alone inside. And since the inside doesn't simplify for an odd exponent and a factor that is not a perfect square, this is going to be my answer. Alright, example 3. We have two fractions underneath the radical. First thing you want to do with fractions is see if you can simplify it. So for our first example, I have 11 over 49. That does not simplify. So we're going to go on to the next step, which is giving each of them their own radical. 11 gets a radical, 49 gets a radical. Now up here, 11 doesn't have any perfect square factors, and it's not a perfect square itself, so I'm going to leave it alone. That's just going to be radical 11. But the bottom, we can take the square root of 49 in our heads. Square root of 49, that's 7. Since I can't do anything else with 11, I've got my answer right here. B example, this one is just the same. I'm going to check to see if I can reduce inside. 12 and 27, both of them are divisible by 3. So 12 turns into 4, and 27 turns into 9. So that takes care of my numbers. My a terms, I have a cubed over a to the first. And if you'll remember from our exponent unit, when you divide, you're subtracting exponents. So we have an a squared in our numerator. Now we're going to do exactly what we did for our a example. Each numerator and each denominator gets their own radical. So I have 9 on the bottom underneath 1, 4a squared underneath 1, and we lucked out because 4 is a perfect square. The square root of 4 is 2. A has an even exponent, which means it's a perfect square. We divide that by 2 to get our answer. 2 divided by 2 is a to the first. And then the square root of 9 is 3. I'm going to check one more time. This can't reduce, so I'm good to go. Alright, example 4, last one's more fractions. They look a little bit different. In A, 2 over 5. I can't do my first step to see if they reduce because 5 is underneath the radical and 2 is not. That radical is kind of like a fortress. You can't do anything until it's taken care of or until everything is underneath. So what I'm going to do, and one big rule for today, you are not allowed to keep a radical in the denominator. No radicals allowed. And let's look back at our example 3s here. If you'll notice, example 3a, there's no radical in the bottom. That's why I was able to circle it. Example 3b, no radical in the bottom. I was allowed to circle it. I can't circle example 4 yet because we're dealing with a radical in the bottom, so I'm going to get rid of it. And if you guys will multiply a radical 5 on the bottom, think about what happens to that. If I say radical 5 times radical 5, that's the same thing as 25 underneath, right? And what happens when you have the square root of 25? That's going to give us 5. So that makes our radical disappear. By multiplying by whatever's underneath the radical here, we're going to get it to disappear. But the rule is, when you're dealing with fractions, if you multiply something in the denominator, you have to multiply the exact same thing in the numerator. So I'm going to have to multiply a radical 5 in the numerator as well. Now when I'm multiplying something outside of a radical and something inside, we're not allowed to mix and match, remember, because that radical is like a fortress. So all we can do is write 2 radical 5. We're going to keep those separate. Can't do anything with those. And since we can't do anything with those, I'm going to bring them over to my last step here. And I have 2 radical 5 over 5. And we're going to see if we can simplify by looking at our numbers that are not underneath the radicals here. We have a 2 and we have a 5. Does that fraction reduce? No, it doesn't. And since it doesn't, that means that our answer is going to be 2 radical 5 over 5. Same thing with B. I cannot reduce 7 over 8n. So I'm going to give them each their own. 7 gets its own radical, and 8n gets its own radical. Now what I'm going to do is look inside each and see if I can simplify these. 7 doesn't simplify. I'm going to drag it over. But if you look at 8n, 8n can simplify because 8 has perfect square factors. 8 factors into 4 times 2. And we all know that 4 is a perfect square. So let's go ahead and do that. The square root of 4 is 2. So that takes care of our 4 here. 2 is not a perfect square. It's going to stay underneath. N has a 1 as an exponent, and since that's odd, we're going to leave that underneath as well. That's just into the first. But that doesn't solve my problem because I still have a radical in the bottom. So what we're going to do is multiply times that radical. I have a radical 2n. And that's going to multiply on top and bottom. I don't have to worry about this 2 because it's not underneath the radical, so it's not breaking any rules. Alright. Let's multiply. Since my 7 and my 2n are both underneath our little fortress here, we can multiply those together. That is allowed. 7 times 2 is 14. On the bottom, I have a 2 that's on the outside. I'm going to leave that on the outside. On the inside, 2 times 2 is 4. N times n is n squared. Let's keep going. Can't do anything with 14n, so we're going to leave that alone. But on the bottom, we've got some perfect squares happening. My 2 that's on the outside is there, but the square root of 4 is 2, and the square root of n squared is n. The last thing to do is just simplify where we can, and the only thing that's going to simplify is our denominator. We're allowed to actually find the product. 2 times n is 4n. Since our 14n is underneath the radical and 4n is not, I can't simplify those, can't do anything with them, and we've gotten our answer. We went through this pretty quickly to make sure that we were under 15 minutes, so if you have any questions, make sure that you ask about them in class so that we can get any and all questions you've got answered.